You are listening to DevOps Unveiled, navigating the modern software development landscape. Subscribe to keep up to date on our latest audiobooks. DevOps Unveiled, navigating the modern software development landscape. 1. A brief history of friction. From silos to collaboration, every grand solution is born from a problem. For modern software development, that problem was friction, a persistent, insidious drag that slowed innovation, bred frustration, and often led to catastrophic failures. To truly understand DevOps, we must first journey back to its origins, examining the landscape that necessitated its emergence. This is a story of well-intentioned methodologies straining under the weight of increasing complexity, and the cultural chasms that formed between the very people tasked with building and running the digital world. The pre-DevOps era, walls not bridges. For decades, the dominant approach to software development was the waterfall model. Imagine a cascade. Requirements flow downwards, then design, then implementation, then testing, and finally, deployment. Each phase had to be completed before the next could begin. On the surface, this seemed logical, orderly, even. But in practice, it was rigid and unforgiving. Bugs discovered late in the testing phase could send the entire project back upstream, wasting significant time and resources. Feedback from actual users often came too late, resulting in products that didn't quite meet market needs. Releases were infrequent, often big bang events that tried to shove months, sometimes years, of changes into production all at once, carrying enormous risk. The inherent limitations of waterfall led to the rise of agile methodologies in the early 2000s. Agile was revolutionary, championing iterative development, continuous feedback, and rapid adaptation. While waterfall was a grand, complex symphony planned years in advance, Agile was more like a jazz ensemble, adapting and improvising based on the immediate rhythm. Developers, working in short sprints, could deliver working software every few weeks, gather user feedback, and quickly pivot. This dramatically improved the speed and responsiveness of the development process itself. However, Agile's success also inadvertently exposed a deeper, often unacknowledged divide within organizations. While developers became increasingly adept at building software quickly, a huge bottleneck remained: actually getting that software into production and keeping it running reliably. This bottleneck was the notorious wall of confusion. On one side stood the development dev teams, driven by innovation, eager to ship new features, working in fast iterations. Their mantra might have been, "Let's build cool stuff and get it out there." On the other side were the operations, ops teams, focused on stability, security, and uptime. Their mantra was often, "Don't break anything. The system needs to run." The metaphor of a high, opaque wall separating these two crucial groups aptly describes the reality. Developers would throw code over the wall to ops, who would then grapple with deployment, configuration, and maintenance, often finding undocumented quirks or incompatible environments. This led to blame games, finger-pointing, and profound inefficiency. Ops would complain that dev didn't understand the complexities of the production environment, while dev would lament ops's slowness and resistance to change. Consider the real-world impact. A development team might complete a new feature in 2 weeks, only for it to sit in a queue for 2 months waiting for an ops team to provision servers, configure databases, and navigate complex change management processes. When it finally went live, often after a late-night manual deployment, it might break because the production environment subtly differed from the developer's machines. The customer, meanwhile, waited impatiently for a feature that was technically done but practically unavailable. The roots of DevOps, breaking down the wall. The growing frustration with this wall of confusion started independently within many organizations. People began asking, if Agile works so well for development, why can't we apply similar principles to operations? This spark led to the Agile infrastructure, or Agile operations movement, where IT operations professionals started to adopt iterative approaches, automation, and continuous improvement practices in their own domain. A pivotal moment arrived in 2009 at the Velocity Conference, an event for web operations and performance. 2 Flickr engineers, John Alspaugh and Paul Hammond, gave a landmark presentation titled 10+ deploys per day. Dev and Ops Cooperation at Flickr. They demonstrated that it was not only possible but beneficial to deploy code to production multiple times a day. Their secret wasn't just technical wizardry, but a deep culture of collaboration between their development and operations teams. This audacious claim, backed by real-world success, sent ripples through the IT community. It showed that the friction was surmountable, and that the benefits of frequent, small releases far outweighed the risks of infrequent, large ones. Inspired by Allspaw and Hammond's talk, a Belgian IT consultant named Patrick Debois organized a series of workshops and discussions in Ghent later that year. He called the event DevOps Days. The name was intentionally coined to emphasize his belief that development and operations should not be separated by a wall, but rather integrated, working collaboratively towards shared goals. And thus, the term DevOps was born. But DevOps wasn't merely a new label. It represented a synthesis of existing powerful ideas that had been brewing across different domains. Lean manufacturing principles. Originating largely from the Toyota production system, Lean focuses on maximizing customer value while minimizing waste. Concepts like flow, smooth, continuous movement of work. Pull. Work is pulled through the system as needed, not pushed, and continuous improvement became highly relevant. In software, this meant reducing wait times, eliminating unnecessary steps, and constantly optimizing the entire value stream from idea to delivery. Systems thinking. Instead of optimizing individual components, e.g., making development faster or operations more stable in isolation, systems thinking suggests that true optimization comes from understanding and improving the entire system. A chain is only as strong as its weakest link. DevOps applied this by urging teams to view the entire software delivery pipeline as one interconnected system, identifying and removing bottlenecks wherever they appeared. In essence, DevOps wasn't an invention out of thin air. It was a natural evolution, a pragmatic response to the challenges of modern software delivery, drawing wisdom from diverse fields. It recognized that the problem was fundamentally cultural and organizational, exacerbated by technological limitations. By blurring the lines between development and operations, embracing automation, and fostering a culture of shared responsibility and continuous improvement, organizations could overcome the historical friction and unlock unprecedented levels of speed, quality, and stability. The why of DevOps is compelling. The next step is to understand the what, the core principles that guide this transformative approach, which we will explore in the following chapter. 2. The DevOps Compass. Understanding its core principles. If Chapter 1 established the why of DevOps, the clear and present need for change, this chapter delves into the what. DevOps is not a product you buy, nor is it a job title. It's a journey, a set of guiding principles, and a philosophy that transforms how organizations create and deliver software. Think of these principles as the cardinal directions on the DevOps compass, essential for navigating the complex terrain of modern technology. At its heart, DevOps is about removing the friction points between developing software and operating it. It aims for a seamless flow of work, rapid feedback, and continuous learning, ultimately leading to faster, more reliable, and more secure software delivery. There are several frameworks that attempt to distill DevOps into its fundamental components. We'll explore two of the most widely recognized, the CALMS framework and the 3 ways of DevOps. The CALMS framework. A comprehensive view. The acronym CALMS serves as a powerful mnemonic for the 5 foundational pillars of DevOps. It reminds us that successful DevOps adoption requires attention to more than just tools or processes. It demands a holistic approach. C is for culture. This is arguably the most crucial and often the most challenging aspect of DevOps. Culture refers to the shared values, beliefs, attitudes, and behaviors within an organization. In a DevOps environment, culture means collaboration and shared responsibility, breaking down the us versus them mentality between development, operations, security, and quality assurance. Everyone is responsible for the product's success and reliability from inception to operation. Trust and empathy. Teams trust each other's expertise and empathize with each other's challenges. Developers understand operational constraints, and operations understand the need for rapid feature delivery. blameless postmortems. When failures occur, and they will, the focus is on understanding what happened, why it happened, and how to prevent recurrence, rather than on who is to blame. This fosters psychological safety, encouraging experimentation and learning. Customer centricity, a shared commitment to delivering value to the end user as quickly and reliably as possible. Without a cultural shift, any technical implementation of DevOps will ultimately fail. You can automate all you want, but if your teams aren't communicating and collaborating effectively, you're merely automating dysfunction. A is for automation. This is where many people mistakenly begin and end their understanding of DevOps. While tools are essential enablers, automation in DevOps is strategic. It's about more than just scripting tasks. It's about making processes repeatable, consistent, and error-free. Key areas of automation include automated builds and testing, ensuring code compiles and passes tests automatically with every change. Automated infrastructure provisioning, spinning up servers, networks, and databases programmatically. Automated deployments, releasing new software versions consistently and reliably to various environments, up to and including production. Automated monitoring and alerting, proactively detecting issues and notifying relevant teams. The goal of automation is not to eliminate human involvement, but to free up valuable human time and intelligence for more complex, creative, and problem-solving tasks. If a task is repetitive, prone to human error, or time-consuming, it's a candidate for automation. L is for lean. Drawing heavily from lean manufacturing principles, this aspect of DevOps focuses on efficiency and value. Lean practices aim to minimize waste, eliminating anything that doesn't add value to the customer or contribute to the final product. This includes unnecessary features, excessive documentation, lengthy approval processes, or waiting times. Maximize value, focusing on delivering features that genuinely benefit the customer. Optimize flow, ensuring a smooth, continuous movement of work through the entire software delivery pipeline, avoiding bottlenecks and delays. Small batch sizes, delivering smaller, more frequent changes, which are easier to test, deploy, and roll back if needed. This reduces risk and accelerates feedback. Think of it like a river. A lean approach creates a wide, smooth river for work to flow through, rather than a narrow, rocky creek filled with obstacles and eddies. M is for measurement. How do you know if your efforts are paying off? By measuring. DevOps emphasizes data-driven decision-making and continuous feedback. This involves collecting data, monitoring system performance, application behavior, deployment frequency, error rates, and user experience. Analyzing metrics, understanding what the data tells you about the health of your systems, the efficiency of your processes, and the satisfaction of your customers. Feedback loops, using insights from measurements to inform future decisions and drive continuous improvement. For instance, if your deployments are frequently failing, measurement highlights this, prompting investigation and improvement. Measurement is not about monitoring individual performance or assigning blame. It's about gaining visibility into the entire system, identifying bottlenecks, and demonstrating the value of DevOps initiatives. S is for sharing. This goes hand in hand with culture and is essential for continuous learning and improvement. Sharing in DevOps involves knowledge sharing, documenting processes, sharing best practices, educating cross-functional teams, and conducting peer reviews. Tooling and infrastructure sharing, standardizing tools and environments across teams to foster consistency and ease collaboration. Communication, open and transparent communication channels between all stakeholders, from developers to operations to business leaders. Feedback sharing, amplifying feedback from users and systems back to the development and operations teams. Sharing ensures that insights gained in one part of the system benefit the whole, building a collective intelligence that drives the organization forward. The 3 Ways of DevOps, a framework for behavioral change, proposed by Gene Kim, Kevin Bayer, and George Spafford in their seminal work The Phoenix Project, and further elaborated in the DevOps Handbook. The 3 Ways of DevOps offer a conceptual framework for the patterns and principles that underpin a successful DevOps culture. These ways describe the core behaviors that teams adopt to improve the flow of work from development to operations. The first way, the flow of work, left to right. This principle focuses on accelerating the delivery of work from its inception, left, all the way through to the customer, right. It's about optimizing the entire software delivery pipeline. Key aspects include system thinking, optimizing for the entire system, not just individual components or teams. Small batch sizes, reducing the amount of work in progress (WIP) and the size of deployments. Smaller changes are less risky and easier to manage. Reduced handoffs, minimizing delays and errors that occur when work passes between different teams. Continuous integration and delivery, automating the process of integrating code, changes frequently, and ensuring the software is always in a releasable state. Imagine a smoothly flowing river. The first way ensures that the river is clear of obstructions, allowing the current to carry work quickly and efficiently downstream to its destination. The second way, the flow of feedback, right to left. This principle emphasizes the importance of rapid, amplified feedback loops from operations, right back to development, left. It's about quickly detecting problems and learning from them. Key aspects include fast and extensive feedback, ensuring that teams receive immediate alerts and information when issues arise in production or during the testing phases. Short feedback loops, the quicker a problem is detected, the faster it can be fixed. Amplified feedback, making sure that critical information reaches the right people quickly and is acted upon. Monitoring and observability, implementing comprehensive monitoring to gather data, detect anomalies, and understand system behavior in real time. Going back to our river analogy, the second way is like having upstream sensors that immediately alert you to changes or blockages downstream, allowing you to react and adapt quickly. It's about getting messages from where the value is consumed back to where it is created. The third way, the flow of continuous learning and experimentation. This principle fosters a culture of continuous improvement, psychological safety, and innovation. It acknowledges that even with the best processes and automation, things will go wrong and opportunities for improvement will always exist. Key aspects include high-trust culture, encouraging experimentation and risk-taking without fear of punishment for honest mistakes. Blameless postmortems, learning from failures by focusing on systemic issues rather than individual shortcomings. Practice and repetition, regularly performing difficult tasks, like deployments, to build muscle memory and identify areas for automation or improvement. Injecting resilience, building fault tolerance and disaster recovery capabilities into systems. Sharing knowledge, spreading lessons learned throughout the organization. The third way transforms mistakes into learning opportunities, making the organization more resilient and adaptable over time. It's about constantly refining the river, learning from every current, every bend, and every obstacle to make its flow even more efficient and robust. The DevOps compass in action. While the CALMS framework and the three ways provide slightly different lenses, they are highly complementary. CALMS gives you the components to focus on culture, automation, lean, measurement, sharing, while the three ways describe the desired behaviors and outcomes within those components: faster flow, better feedback, continuous learning. Together, these principles form the very foundation of DevOps. They are not merely theoretical constructs, but actionable guidelines that inform every practice, every tool choice, and every team interaction in a truly DevOps organization. Understanding these core principles is the crucial first step on your journey to navigating the modern software development landscape. Armed with this compass, we can now begin to explore the practical applications and building blocks of a DevOps pipeline, starting with the very first stage: planning and version control. 3. The continuous flow: planning, collaboration, and version control. With the theoretical compass of DevOps firmly in hand, it's time to start our practical journey through the continuous software delivery pipeline. Every great endeavor begins with meticulous planning, and software development is no exception. In a DevOps world, however, planning transcends isolated departmental tasks. It becomes a collaborative, integrated process that sets the stage for continuous flow. The start of the value stream, from idea to commit. In traditional settings, the journey of a new feature often begins with a business analyst defining requirements, then passing them to development, who then pass them to testing, and so on. In DevOps, the emphasis shifts to a shared understanding of value and a more unified approach to managing the work. The goal is to ensure that every piece of work, from a new feature to a bug fix or an operational improvement, is clearly understood by everyone involved, and that its progression is as smooth as possible. This starts with collaborative planning. Collaborative planning, beyond departmental silos. In a DevOps context, planning is not just for the development team. It's an exercise that naturally brings together representatives from development, operations, quality assurance, and even security right from the outset. This shift-left approach, applying principles earlier in the lifecycle, ensures that operational readiness, security considerations, and quality requirements are baked into the plan, not tacked on as afterthoughts. This integration often manifests using agile methodologies like Scrum or Kanban. Scrum ceremonies, like sprint planning, daily stand-ups, and sprint reviews, become opportunities for cross-functional teams to discuss work items, clarify requirements, and anticipate potential challenges from an operational or security perspective. Kanban boards provide a transparent view of work in progress, allowing everyone to see bottlenecks, understand priorities, and collaborate on unblocking issues, whether they are development tasks, infrastructure provisioning, or security configurations. The aim is to maintain a unified backlog, a single prioritized list of all work items for a product or service. This backlog includes not just new features, but also technical debt, operational tasks, like upgrading a database or configuring monitoring, and security hardening. This ensures that the collective effort is always directed towards the most valuable items for the business and the customer, balancing new feature delivery with system health and reliability. Version control as the foundation, the DNA of your codebase. Once a work item is planned, it needs to be translated into executable code and configurations. This is where version control comes in, forming the absolute bedrock of a DevOps pipeline. Think of a version control system, VCS, as the definitive record keeper for your entire codebase, including application code, configuration files, infrastructure definitions, and even documentation. Without it, continuous integration, continuous delivery, and collaboration at scale would be impossible. Why is version control so critical in a DevOps paradigm? Single source of truth. It provides a centralized, authoritative repository for all code. Everyone works from the same foundation. History and auditability. Every change, no matter how small, is recorded, who made it when and often why. This creates an invaluable audit trail and allows you to trace problems back to their source. Collaboration. Multiple developers, and increasingly, operations and security engineers, can work on the same codebase simultaneously without overwriting each other's changes. Rollback capability. If a change introduces an error, you can quickly revert to a previous, known good state. This is crucial for maintaining system stability and rapid recovery. Foundation for automation. Automated pipelines rely on the version control system to detect changes, trigger builds, run tests, and deploy code. While many VCS options exist, Git has become the undisputed de facto standard in modern software development. Its distributed nature, where every developer has a full copy of the repository on their local machine, makes it incredibly powerful for offline work, fast operations, and robust branching strategies. Core Git concepts to understand. Repository, the central storage location for your project's files and their revision history. Commit, a snapshot of your changes to the repository at a specific point in time. Each commit has a unique identifier and a message describing the change. Branch, a parallel line of development. Branches allow developers to work on new features or bug fixes independently without affecting the main codebase. Merge rebase, operations to integrate changes from one branch into another. Pull request, PR, merge request, MR. A mechanism for proposing changes to a repository and requesting that others review those changes before they are merged into a main branch. PRs are a critical step for quality control and knowledge sharing. Branching strategies, facilitating continuous integration. How teams use branches significantly impacts their ability to practice continuous integration, which we'll cover in the next chapter. Common strategies include feature branching. Each new feature or bug fix gets its own long-lived branch. While this offers isolation, it can lead to merge hell if branches diverge too much from the main codebase over time, slowing down integration. Git flow, a more complex prescriptive model with dedicated branches for features, releases, and hotfixes. While robust, its complexity can sometimes slow down rapid, continuous delivery. Trunk-based development, TBD. This strategy is highly recommended for DevOps. Developers commit their small, isolated changes directly to a single main branch, often called main or master, multiple times a day. If a change can't be immediately merged, it is developed on a very short-lived branch that is merged back quickly. TBD inherently pushes towards continuous integration, as changes are constantly being integrated and tested against the main branch, minimizing integration issues. In a TBD environment, the emphasis is on making very small, frequent commits. When a feature is large and can't be broken down into tiny, independent pieces, feature flags, or feature toggles become invaluable. A feature flag allows you to merge incomplete code into the main branch, but keep the feature off or hidden from users until it's fully developed and tested. This decouples code deployment from feature release, enabling continuous delivery even for larger changes. Code reviews, a shared responsibility for quality. Before changes are permanently integrated into the main branch, they typically undergo a code review. This is a collaborative process where one or more team members examine the proposed changes. Code reviews are not just about finding bugs, they are also about knowledge sharing, spreading understanding of the codebase. Mentorship, experienced developers can guide less experienced ones. Consistency, ensuring adherence to coding standards and best practices. Finding logical flaws, catching issues that automated tests might miss. Building collective ownership, fostering a sense of shared responsibility for the quality of the codebase. Early integration, the key to unlocking value. The principles of collaborative planning and robust version control form the initial crucial steps in the continuous flow of DevOps. By embracing unified backlogs, cross-functional collaboration, and especially trunk-based development with frequent, small commits, teams set themselves up for success. This approach ensures that work flows left to right from conception, through code, into a state where it is ready for the assembly line of automated building and testing, the essence of continuous integration, which we will uncover next. 4. The assembly line, continuous integration explained. In the previous chapter, we established the foundational role of planning, collaboration, and version control, particularly the practice of committing small, frequent changes to a main branch. This disciplined approach sets the stage for the next crucial link in the DevOps chain, continuous integration, CI. If version control is the DNA of your code, then continuous integration is the automated assembly line that ensures that DNA can always build a healthy organism. What is continuous integration, CI? At its core, continuous integration, CI, is a development practice where developers frequently integrate their code changes into a shared main branch. Each integration is verified by an automated build and automated tests, allowing teams to detect integration errors early and rapidly. Historically, integration was a painful and time-consuming process. Developers would work on their features for days or weeks, then attempt to merge their large, divergent codebases. This often led to integration hell, where numerous conflicts, broken dependencies, and unexpected behaviors would appear. Fixing these issues could take days, delaying releases and fostering a culture of fear around integration. CI was born to solve this problem. The essence of CI can be broken down into these principles. Frequent integration. Developers commit changes to the main branch multiple times a day, ideally at least once per day. Automated build. Every change triggers an automated process that compiles the code, resolves dependencies, and creates executable artifacts, e.g., a jar file, a Docker image, a web application package. Automated testing. A battery of automated tests, primarily unit tests and static analysis, runs immediately after a successful build to verify the correctness of the new changes and ensure they haven't broken existing functionality. Immediate feedback. If the build or tests fail, the team is notified immediately, usually within minutes. This rapid feedback is critical for quickly identifying and fixing problems. The CI workflow in action. Let's walk through a typical CI workflow. Developer commits code. A developer, having completed a small, isolated change, like a new function or a bug fix, commits their changes to the shared version control repository, e.g. Git. This commit is small and focused, often addressing a single task or user story. Version Control System, VCS, notifies CI server. The VCS, upon receiving the commit, typically sends a notification, a webhook, to a dedicated CI server. CI server triggers build. The CI server picks up the changes, checks out the latest code from the main branch, and initiates an automated build process. This could involve compiling source code, packaging application components, or generating documentation. Automated tests run. After a successful build, the CI server automatically executes a suite of automated tests. The most common type at this stage are unit tests, which verify individual components or functions of the code in isolation. Static analysis tools might also run here to check for coding standards violations, security vulnerabilities, or logical errors without actually executing the code. Artifact generation, optional but recommended. If all builds and preliminary tests pass, the CI server often generates a deployable artifact. This artifact is a self-contained package of the application and its dependencies, ready to be deployed to various environments. Crucially, this identical artifact will be used for all subsequent stages of testing and deployment, ensuring consistency. Feedback notification. Success. If all steps complete successfully, the CI server notifies the team, e.g., via a green checkmark in the version control system, a message in a team chat, or an email that the build is green. This means the main branch is in a healthy, working state. Failure. If any step fails, e.g., code doesn't compile, a unit test breaks, static analysis finds a critical error, the CI server immediately notifies the team. The build is red. The team's immediate priority shifts to fixing the red build. This is because a broken build halts the continuous flow for everyone. A core tenet of CI is that a broken build must be fixed immediately before any new features are added. This collective commitment ensures that the main branch is always in a releasable state. Key benefits of continuous integration. Embracing CI offers a multitude of advantages that directly contribute to faster, more reliable, and higher quality software delivery. Early detection of bugs and conflicts, the most significant benefit. By integrating frequently, conflicts are small and immediate, making them significantly easier and cheaper to fix than large, accumulated integration issues. Reduced integration risk. Integration hell becomes a relic of the past. The system is always in a known, working state. Improved code quality. Automated tests and static analysis act as a safety net, encouraging developers to write cleaner, more maintainable code. The constant feedback loop helps maintain coding standards. Faster release cycles. With a continuously integrated and tested codebase, the software is always potentially releasable, shortening the time from development to production. Increased team confidence. Teams gain confidence in their ability to deliver working software rapidly and reliably, reducing stress associated with releases. Green build as a shared goal. The visible status of the build, green or red, becomes a collective responsibility and a clear indicator of the project's health. Teams rally to keep the build green. Common CI tools, conceptual overview. While this book focuses on principles rather than specific tool instructions, it's useful to be aware of the types of tools that enable CI. Jenkins, a highly extensible open-source automation server that can orchestrate a wide variety of build, test, and deployment tasks. GitLab CI/CD, built directly into the GitLab platform, providing integrated version control, CI/CD, and more. GitHub Actions, similarly integrated into GitHub, enabling automated workflows directly within repositories for CI/CD. Azure DevOps Pipelines, Microsoft's comprehensive suite offering CI/CD capabilities, project management, and more. Travis CI/Circle CI/Atlassian Bamboo. Other popular CI/CD platforms with robust capabilities. These tools manage the orchestration of the CI process, triggering builds, running tests, and providing feedback. They are the engines of the assembly line. Anti-patterns to avoid. Even with the best intentions, certain practices can undermine the effectiveness of CI. Infrequent commits. If developers wait days to commit their code, they negate the benefits of early conflict detection. Ignoring broken builds. Allowing the build to remain red for extended periods signals a lack of commitment to quality and stops the continuous flow. Long-lived feature branches. While sometimes necessary, extended branches increase the risk of merge conflicts and integration issues, especially when not using feature flags. Insufficient automated tests. If the test suite is too sparse, many integration issues will slip through, undermining the confidence CI is supposed to build. Continuous integration is the heartbeat of the DevOps pipeline. By continuously blending individual changes into a robust, unified whole, it transforms software development from a series of disjointed activities into a smooth, efficient, and reliable assembly line. However, a quality assembly line isn't just about putting things together. It's also about rigorously checking them at every step. This leads us to the critical role of continuous testing strategies, which we will explore in the next chapter. 5. The quality gate, continuous testing strategies. In our journey through the DevOps pipeline, we've established the importance of version control and the automated assembly line of continuous integration, CI. CI ensures that code changes are frequently merged and automatically built. But a successful assembly line isn't just about putting pieces together. It's about rigorously inspecting the quality of those pieces and the final product at every stage. This is where continuous testing steps in, acting as the crucial quality gate within the DevOps philosophy. Continuous testing is the process of executing automated tests as part of the software delivery pipeline to obtain rapid feedback on the business risks associated with a software release candidate. In a DevOps environment, testing is no longer a separate phase at the end of the development cycle. It's an integrated, ongoing activity that shifts left, meaning it occurs earlier and more frequently in the development lifecycle. Beyond unit tests, the testing pyramid. In Chapter 4, we discussed how unit tests are run as part of the CI process, providing immediate feedback on small code changes. However, unit tests alone are not sufficient to guarantee quality. They test individual components in isolation, but they don't verify how these components interact, how the system behaves under load, or how a user experiences the application. To address this, we often refer to the testing pyramid, a concept popularized by Mike Cohn. It suggests a balanced approach to test automation, with different types of tests forming layers, each with varying scopes, speeds, and costs. Unit tests, base of the pyramid. Scope, test very small, isolated units of code, functions, methods, classes. Speed, extremely fast, running in milliseconds. Cost, relatively inexpensive to write and maintain. Purpose, verify the correctness of individual code logic. They form the vast majority of tests in a well-tested application. Integration in CI, run with every code commit. Integration tests, middle layer. Scope, test how different components or services interact with each other, e.g., an application module interacting with a database or two microservices communicating. Speed, faster than end-to-end tests, slower than unit tests. Cost, more complex to set up and maintain than unit tests. Purpose, verify the correct communication and data flow between interacting parts of the system. API tests, part of the middle layer. Scope, test the application's programming interfaces, APIs directly without a graphical user interface. Speed, relatively fast. Cost, more stable and less brittle than UI tests. Purpose, verify the functionality, reliability, performance, and security of API endpoints, which are often the backbone of modern applications. UI end-to-end tests, top of the pyramid. Scope, simulate actual user interactions with the complete application through its user interface. Speed, the slowest of all tests, often running in minutes. Cost, most expensive to write, execute, and maintain, often brittle and prone to breakage with UI changes. Purpose, provide confidence that the entire system works as expected from a user's perspective. These should be kept to a minimum due to their flakiness and cost. The pyramid shape suggests that you should have many fast, isolated unit tests, fewer integration API tests, and very few slow, expensive UI tests. This hierarchy optimizes for speed of feedback and cost efficiency without sacrificing coverage. The role of automation in testing. Manual testing, while sometimes necessary for exploratory testing or complex user experience, UX evaluation, is a significant bottleneck in a continuous delivery pipeline. It's slow, expensive, prone to human error, and inconsistent. In DevOps, automation is king for all recurring tests. Automated tests can be run consistently, rapidly, and repeatedly, providing immediate and reliable feedback. Key continuous testing strategies. Beyond the pyramid, several strategic approaches ensure quality throughout the pipeline. Test-driven development, TDD. A development practice where developers write failing automated tests before writing the code itself. The goal is to write just enough code to make the test pass, then refactor. TDD improves code quality, design, and provides immediate feedback. Behavior-driven development, BDD. An extension of TDD that focuses on collaboration between developers, quality assurance, and non-technical stakeholders. Tests are written in a human-readable format, e.g., Gherkin syntax. Given, when then, describing the desired behavior of the system from the user's perspective. This ensures everyone has a shared understanding of what needs to be built and tested. Performance testing. Once an application is generally functional, it's crucial to understand how it behaves under various conditions. Automated performance tests simulate user load, stress points, and scalability limits. This includes load testing, assessing system behavior under anticipated load. Stress testing, determining how the system performs under extreme conditions. Scalability testing, checking the application's ability to handle increasing user or data volumes. Running these tests periodically in the pipeline helps catch performance regressions early, long before they impact users in production. Security testing, shift left. Traditionally, security testing was a late-stage activity, often carried out by a separate security team. In DevOps, security is shifted left, meaning it's integrated throughout the SDLC. Automated security tests become part of the continuous testing strategy. Static application security testing, SAST, analyzes source code, bytecode, or binary code to detect security vulnerabilities without executing the program. Runs early in the CI pipeline. Dynamic application security testing, DAST, analyzes a running application from the outside, simulating attacks to find vulnerabilities. Runs later in the pipeline, perhaps in a staging environment. Software composition analysis, SCA, scans the application's dependencies, open source libraries, third-party components for known vulnerabilities. Container security scanning ensures that Docker images or other container artifacts don't contain known vulnerabilities. Test data management. A common challenge in continuous testing is managing realistic and consistent test data. Strategies involve creating synthetic data, masking sensitive production data, or refreshing test databases automatically as part of the pipeline. Key principles of continuous testing. Test often, test early, test everywhere. Integrate testing into every possible stage of the development and delivery process. Automate everything feasible. Minimize manual testing for repeatable, regression-prone tasks. Rapid feedback. Ensure tests run quickly and provide immediate results to developers. Reliable and consistent. Tests should yield consistent results given the same input, preventing flaky tests that unpredictably fail. Whole team approach. Quality is everyone's responsibility, not just the QA teams. By implementing these continuous testing strategies, software development teams build confidence in every release candidate. The automated tests act as a series of quality gates, ensuring that only robust, high-quality, and secure code progresses down the pipeline. This proactive approach not only reduces risks, but also forms the confidence needed to move to the next critical stage, seamlessly delivering ready-to-deploy software to production environments through continuous delivery and deployment. 6. The deployment pipeline, continuous delivery and deployment. We've journeyed from collaborative planning and diligent version control through the automated assembly line of continuous integration and the rigorous quality gates of continuous testing. Now we arrive at the culmination of the DevOps pipeline, getting the validated software into the hands of users. This is the domain of continuous delivery, CD, and its more advanced cousin, continuous deployment, CD. While often used interchangeably, there's a crucial distinction that reflects different levels of automation and trust. Defining continuous delivery, CD. Continuous delivery, CD, is an engineering discipline where software is always in a deployable state throughout its lifecycle. This means that at any point in time, the code that has passed through the CI and automated testing stages is ready to be released to production at the push of a button. The key characteristic here is the readiness for deployment, not necessarily the act of immediate deployment. In a continuous delivery setup, every code change that successfully passes the automated build and test suite results in a deployable artifact, e.g., a new version of your application. This artifact is then moved through a series of increasingly rigorous automated tests and environments, e.g., staging, pre-production. The final step of deploying to production is a manual decision, often triggered by a human pressing a button, verifying a change, or scheduling a release window. The benefits of continuous delivery are profound. Ability to release on demand. The software is always in a releasable state, allowing businesses to respond quickly to market needs, customer feedback, or competitive pressures. Reduced risk. By deploying smaller changes more frequently, the risk associated with each deployment is significantly reduced. Debugging problems becomes easier as there are fewer changes to analyze. Faster feedback. Getting new features into the hands of users quicker means gaining real-world feedback sooner, allowing for quicker iteration and course correction. Improved quality. The rigorous automated build and test process inherent in CD catches issues early, preventing costly defects from reaching production. Defining continuous deployment, CD. Continuous deployment, CD, takes continuous delivery a step further. In continuous deployment, every change that successfully passes all automated tests and quality gates is automatically deployed to production without human intervention. The only reason a change wouldn't go to production is if it fails one of the automated checks. This level of automation requires an extremely high degree of trust in the automated testing suite and the entire pipeline. It means that if a developer commits code and it passes all automated tests, it will be live for users within minutes or at most a few hours. The advantages of continuous deployment include fastest time to market. New features and bug fixes reach users almost instantly. Increased throughput. More changes can be delivered to production per unit of time. Removes human error in deployment. Reduces the possibility of manual misconfigurations during release. Forces stronger automation and testing. The sheer pace makes it impossible to rely on manual steps, driving teams to invest heavily in robust automation and comprehensive test coverage. While continuous deployment represents the pinnacle of automation, it's not always suitable for every organization, especially those with stringent regulatory requirements or extremely sensitive systems. Many organizations start with and effectively utilize continuous delivery before gradually moving towards continuous deployment as their confidence in automation and testing matures. The CD pipeline stages in practice. Regardless of whether you choose continuous delivery or continuous deployment, the core concept is the deployment pipeline. This pipeline is the automated manifestation of your software release process. It ensures consistency, repeatability, and reliability by defining a series of automated stages that a build must pass through on its way to production. A typical deployment pipeline might include stages like source control and build CI, as covered in Chapter 4, Code Committed to Version Control, triggering an automated build and unit tests. Automated acceptance tests. As covered in Chapter 5, the newly built artifact is deployed to a test environment, often ephemeral, where more comprehensive automated tests run, including integration, API, and a small suite of critical UI tests. Performance security scans, automated performance tests, load, stress, and security scans, DASD, are run to ensure the application meets non-functional requirements and is free of major vulnerabilities. Staging pre-production environment. The artifact is deployed to an environment that closely mirrors production. Here, more extensive and potentially longer-running tests might occur, including exploratory testing, user acceptance testing, or complex end-to-end scenarios. This is often the final automated gate before production. Production deployment, the final step where the artifact is released to the live user environment. Crucially, each stage in the pipeline serves as a quality gate. If a stage fails, the pipeline halts, and the team is immediately notified, preventing unhealthy code from progressing further. Key capabilities for successful CD/CD. To effectively implement continuous delivery or deployment, several technical and procedural capabilities are essential. Idempotent deployments. Deployments must be repeatable and yield the same result every time. Running the same deployment script multiple times should not cause unintended side effects. This depends heavily on infrastructure as code, Chapter 7. Automated rollbacks, the ability to quickly and reliably revert to a previous, stable version of the application if a deployment introduces critical issues. This minimizes downtime and significantly reduces the risk of new releases. Feature flags/feature toggles. As mentioned in Chapter 3, these allow development teams to deploy new code to production while keeping certain features hidden or disabled for users. This decouples deployment from release, enabling small, frequent deployments without impacting user experience until a feature is ready and toggled on. They also allow for A/B testing and phased rollouts. Canary deployments, a low-risk deployment strategy where a new version of the application is rolled out to a small subset of users, the canary group, before being deployed to the entire user base. Monitoring tools, Chapter 8, are closely watched during this period. If issues arise, the deployment to the canary group can be easily rolled back, limiting the impact. Blue-green deployments. This strategy involves running two identical production environments: a blue environment, the current live version, and a green environment, the new version. When the new version is ready, traffic is seamlessly switched from blue to green. If problems occur, traffic can be instantly switched back to blue, providing near-zero downtime rollbacks. Challenges and overcoming them. While the benefits are clear, implementing continuous delivery deployment comes with its challenges. Building trust in the pipeline. Teams must have unwavering confidence that the automated tests and gates accurately reflect production readiness. This involves constant refinement of testing strategies. Dealing with legacy systems, older systems with complex dependencies or manual deployment processes can be difficult to integrate. Incremental adoption, focusing on small changes and building adapters are common strategies. Database migrations. Managing database schema changes in a way that is compatible with both the old and new versions of the application. If a quick rollback is needed, requires careful planning and automation. Cultural resistance. Moving from infrequent, large releases to frequent, small ones can be a significant cultural shift. Continuous delivery and deployment represent a fundamental shift in how organizations release software. They are the ultimate expression of the flow principle in DevOps, ensuring that every validated change moves swiftly and reliably into the hands of users. However, for this pipeline to function effectively, it needs a rock-solid foundation, consistent, repeatable infrastructure. That's where infrastructure as code takes center stage. 7. Infrastructure as code, building resilient environments. We've now seen how continuous integration and continuous delivery enable a rapid, reliable flow of software through an automated pipeline. But what about the environments where this software actually lives and breathes? The servers, networks, databases, and configuration settings that make up the operational landscape. For many years, provisioning and managing this infrastructure remained a largely manual, error-prone, and slow process. becoming a significant bottleneck in the very pipelines DevOps aimed to accelerate. This brings us to a revolutionary practice: infrastructure as code, ISC. The problem with manual infrastructure. Imagine a scenario where a development team has just perfected a new application feature. They've pushed it through CI, it's passed every automated test, and it's now awaiting deployment to a staging environment for final checks. But the staging environment is often configured manually by an operations engineer, a series of clicks in a cloud console, or commands typed into server terminals. This manual process introduces several critical problems: inconsistency, configuration drift. Each environment, development, test, staging, production, can subtly differ. A configuration setting might be missed, a dependency installed incorrectly, or a security group misconfigured. These subtle differences often lead to the infamous "it works on my machine" problem, only now it works in staging, but not in production. These inconsistencies are notoriously hard to debug. Snowflake servers. Over time, manually managed servers accumulate unique configurations and patches, making them snowflakes, each one slightly different from the others. If one fails, it's incredibly difficult to replicate, let alone replace precisely. Human error. Manual processes are inherently susceptible to human error. A typo, a forgotten step, a misinterpretation of instructions. Slow provisioning. Setting up new environments or scaling existing ones can take days or weeks, directly undermining the speed benefits of CI/CD. Lack of auditability. Without a codified, version-controlled record, it's hard to track who changed what, when, and why in the infrastructure. What is infrastructure as code, ISC? Infrastructure as code, ISC, is the practice of managing and provisioning computing infrastructure through machine-readable definition files, rather than through manual hardware configuration or interactive configuration tools. Essentially, you define your desired infrastructure: servers, networks, storage, applications, etc. in code, treat it like any other software artifact, and manage it using version control systems. The core benefits of adopting ISC are compelling: consistency and repeatability. The infrastructure definition is codified, so recreating an environment produces an identical, consistent result every time. This ensures parity across development, test, staging, and production environments, eliminating "it works on my machine" issues. Speed and efficiency. Automating infrastructure provisioning dramatically reduces setup time from days, weeks to minutes, hours. This enables developers to spin up environments on demand, accelerating development and testing. Version control and auditability. Because infrastructure is code, it can be versioned, allowing teams to track changes, revert to previous configurations, and review additions or modifications. This provides an invaluable audit trail. Collaboration. Just like application code, infrastructure code can be shared, reviewed, and collaborated on by multiple team members, fostering a shared understanding and ownership. Reduced risk. Automated, consistent deployments reduce human error. If an environment becomes corrupted, it can be quickly and reliably destroyed and rebuilt from its ISC definition. Core concepts in ISC: declarative versus imperative. Declarative ISC, you describe the desired state of your infrastructure. The ISC tool then figures out the steps to achieve that state. This is highly idempotent. E.g., I want a server with these specifications and this software installed. Imperative ISC, you describe the steps needed to get to a certain state. E.g., first create a server, then install Apache, then copy these files. Most modern ISC tools allow for both, but declarative approaches are generally preferred for their simplicity and robustness. Idempotence, a key characteristic of robust ISC. Applying the same configuration or script multiple times will produce the same result as applying it once. This is crucial for automation, as you might run a configuration script repeatedly without concern for side effects. Immutability, the concept of never modifying infrastructure once it's deployed. If a change is needed, a new, updated instance is created from scratch using the ISC, and the old instance is discarded. This reduces configuration drift and makes environments more predictable and reliable. Types of ISC tools. Conceptual overview. The ISC ecosystem is rich and diverse, with tools often specializing in different aspects of infrastructure management. Provisioning tools, used to provision the underlying infrastructure resources, servers, databases, networks in cloud providers. Terraform, cloud-agnostic and powerful, allowing you to define infrastructure for various cloud providers, AWS, Azure, Google Cloud, and on-premises environments using a single declarative language, HCL. CloudFormation, AWS, Azure Resource Manager, Azure, Google Cloud Deployment Manager, GCP, cloud-specific ISC tools provided by cloud vendors. Pulumi allows you to define infrastructure using familiar programming languages, Python, JavaScript, Go, C#. Configuration management tools, used to configure operating systems, install software, and manage services on existing servers. Ansible, agentless, human-readable, YAML-based, and highly popular for its simplicity and power. It manages configuration by pushing changes to target machines. Chef and Puppet, agent-based solutions where an agent runs on each server, regularly checking that its configuration matches the desired state defined in central cookbooks or manifests. SaltStack combines aspects of both agent-based and agentless approaches, known for its speed and scalability. Container orchestration. While not strictly ISC in the traditional sense, platforms like Kubernetes embody the ISC principle by allowing you to declaratively define the desired state of your applications and their supporting infrastructure, like networking and storage volumes. Kubernetes then continuously works to ensure the cluster's actual state matches this desired state. Network as code/security as code. ISC principles extend beyond just servers. Tools and practices are emerging to define network configurations, routers, firewalls, load balancers, and security policies, firewall rules, access control as code, bringing the same benefits of version control, automation, and consistency to these critical areas. Implementing ISC in the DevOps pipeline. Integrating ISC into your DevOps pipeline transforms how you manage environments. Version control ISC. Store all infrastructure definitions in your version control system, Git, alongside your application code. Automated provisioning. Use your CI/CD pipeline to automatically provision or update environments based on your ISC definitions. This means that when a new feature branch is created, a dedicated test environment can be spun up automatically. Destruction and rebuilding. With ISC, environments can be treated as ephemeral. Rather than spending time troubleshooting a flaky test environment, it can be automatically destroyed and rebuilt from its code definition in minutes, ensuring a clean slate. Self-service. Developers can be empowered to provision their own development or test environments on demand, without waiting for the operations team, as long as they use the defined ISC templates. Consider the case of QuickShip Logistics, the fictional company we introduced earlier. Their IT department used to take weeks to provision a new server, leading to delays and inconsistent environments. By adopting ISC, they define their server configurations, network settings, and application dependencies in Terraform and Ansible scripts. Now, when a new project starts, a developer can trigger a pipeline that automatically provisions a complete development environment in under an hour, identical to potential staging and production setups. This dramatically accelerated their project timelines and eliminated configuration-related bugs. Infrastructure as code is a cornerstone of modern DevOps. By treating infrastructure definitions as code and subjecting them to the same rigorous practices as application code, version control, automated testing, continuous integration, organizations gain unprecedented levels of speed, consistency, and reliability in their environments. With infrastructure now managed programmatically, the next step is to ensure that once deployed, applications are not only running, but also telling us how well they are performing. This brings us to the crucial feedback loop of monitoring, logging, and observability. 8. The feedback loop, monitoring, logging, and observability. We've covered the first two pillars of the 3 ways of DevOps, optimizing the flow of work, from planning to continuous delivery, and enabling fast feedback from our automated pipeline. Now that our software is built, tested, and reliably deployed onto infrastructure managed as code, the real journey begins, understanding how it behaves in the wild. This brings us to the second of the three ways, the flow of feedback. In any complex system, things will inevitably go wrong. The mark of a mature DevOps organization isn't that nothing ever fails, but rather how quickly it detects, diagnoses, and recovers from failures, and how effectively it learns from them. This crucial feedback loop is powered by robust monitoring, logging, and observability practices. The importance of feedback, learning from production. Once an application is in production, it's interacting with real users, real data, and real-world conditions. This is where the rubber meets the road. Feedback from the production environment is invaluable for fast problem detection, identifying issues the moment they occur, minimizing impact on users. Rapid diagnosis and resolution, understanding why a problem is happening and fixing it quickly. Understanding system behavior, gaining insights into how the application performs under various loads, network conditions, and user patterns. Validating assumptions, confirming whether new features are being used as expected and delivering the intended value. Continuous improvement, using insights from production to inform future development, infrastructure decisions, and security enhancements. Without effective feedback mechanisms, you're flying blind. You wouldn't drive a car without a speedometer or fuel gauge. Similarly, you shouldn't run a complex software system without clear indicators of its health and performance. Monitoring versus observability, a key distinction. While often used interchangeably, there's a subtle but important distinction between monitoring and observability in the context of modern distributed systems. Monitoring. This typically involves collecting predefined metrics and logs to answer known questions about the system's health. You set up alerts for specific thresholds, e.g., CPU utilization above 90%, disk space critically low, error rate spikes. Monitoring tells you what is happening. It's like the dashboard of your car, speed, fuel level, engine light pre-selected gauges telling you the operational status. Example. An alert triggers because the application's error rate has jumped from 1% to 10%. Monitoring tells you that the error rate is high. Observability. This is a much broader concept. An observable system allows you to understand why something is happening without prior knowledge of the issue. You can ask arbitrary questions about the system's internal state purely by examining the data it outputs, metrics, logs, and traces. Observability is about gaining deep insights and being able to explain complex, emergent behaviors. It's like having access to all the raw sensor data from your car, allowing you to debug an intermittent engine problem even if it's not triggering a predefined warning light. Example, with an observable system, you can then drill down from the high error rate to identify the specific microservice experiencing issues, the exact API endpoint failing, the relevant log messages, and even the trace of a single failing request across multiple services, immediately pinpointing the root cause, e.g., a specific database query timing out. The three pillars of observability. To achieve true observability, a system needs to emit and process three primary types of telemetry data. Metrics, quantitative measurements collected over time, often aggregated. They are ideal for quick numerical insights into system behavior, trends, and alerts. Examples: CPU utilization, memory consumption, network latency, request rates, requests per second, error rates, number of active users, queue lengths, transaction duration. Tools conceptual, Prometheus, InfluxDB, Grafana for visualization. Logs, detailed, time-stamped records of events that occur within the application or infrastructure. Logs provide context and specific information about what happened at a given moment. In modern distributed systems, structured logging, JSON format, is preferred for easier parsing and analysis. Examples: user login attempts, database query failures, configuration changes, system warnings, application-specific events. Tools conceptual, Elasticsearch, Logstash, Kibana, Elk Stack, Splunk, Sumo Logic. Low-key for log analytics. Traces represent the end-to-end journey of a single request or transaction as it propagates through a distributed system, spanning multiple services, databases, and network hops. traces are crucial for understanding performance bottlenecks and failures in microservices architectures. Examples: a user clicks a button, which triggers a request to service A, which calls service B and database C before returning a response to the user. A trace visualizes this entire flow, showing timings for each step. Tools: conceptual, Jaeger, Zipkin, OpenTelemetry. Alerting and dashboarding, making feedback actionable. Once you're collecting vast amounts of telemetry, you need ways to make it actionable. Alerting, setting up rules to notify teams when specific conditions are met that indicate a potential problem. Good alerting is crucial for immediate problem detection. Principle: alert on symptoms, what's broken for the user, rather than causes, what's broken in the system. This helps avoid alert fatigue and ensures teams are notified about real user-impacting issues. Example: instead of alerting if CPU usage is high, alert if request latency reaches an unacceptable level for users. Dashboarding, visualizing key metrics and log data in real time or near real time. Dashboards provide a comprehensive overview of system health, performance trends, and business metrics. They help teams quickly understand the current state and identify patterns. Feedback loop in practice. A blameless postmortem. Let's revisit the concept of a blameless postmortem from Chapter 2 through the lens of observability. Imagine the fictional company, QuickShip Logistics, has an issue where their customer tracking service occasionally returns internal server error. Metric alert. A metric dashboard shows an alarming spike in error rates for the tracking service. An alert fires to the on-call team. Monitoring in action. Log review. The team immediately dives into the logs for the tracking service. They filter logs for the error messages and correlated timestamps, seeing a pattern of database connection timeouts. Leveraging granular log data. Trace analysis. They use a tracing tool to examine a few of the failed requests. The trace clearly shows that the bottleneck is a specific database query taking an unusually long time, leading to connection exhaustion. Pinpointing issues in distributed systems. Root cause and resolution. With this data, the team diagnoses a recent database index change that inadvertently degraded performance for certain queries. They quickly revert the index or apply a patch. Postmortem and learning. After resolution, a blameless postmortem meeting is held. They use the metrics, logs, and traces to reconstruct the incident. They identify systemic issues, e.g., inadequate integration testing for database changes, missing performance test, scenario for this query pattern, insufficient database connection pooling, and implement improvements to prevent recurrence. This includes adding a new automated performance test to their CI/CD pipeline. Closing the feedback loop for continuous learning. This iterative process, measure, alert, investigate, fix, learn, improve, is the continuous feedback loop in action. It ensures that every incident becomes a learning opportunity, driving resilience and continuous improvement throughout the entire DevOps lifecycle. By embracing robust monitoring, comprehensive logging, and deep observability, organizations can transform their operations from reactive firefighting to proactive, data-driven resilience, constantly refining their systems based on real-world performance. This strong feedback loop also provides a critical safety net for the next crucial area we need to integrate: security. 9. Securing the pipeline, integrating DevSecOps. Throughout our exploration of the DevOps pipeline, from collaborative planning to automated deployment and comprehensive feedback, we've often hinted at the importance of security. Traditionally, security was often viewed as a separate, gatekeeping function, typically applied towards the very end of the software development lifecycle. This throw security over the wall approach, much like the throw operations over the wall problem, created bottlenecks, slowed down releases, and resulted in costly, late-stage fixes. In the fast-paced world of DevOps, this approach is simply untenable. This is where DevSecOps comes in. DevSecOps is the natural extension of DevOps, embedding security practices and considerations throughout every stage of the software development lifecycle. It's about making security an integral, explicit, and automated part of the entire pipeline rather than an afterthought. The core principle is to shift security left, meaning integrate security from the very first planning stages, rather than waiting until just before deployment. Why DevSecOps? The imperative for integrated security. The traditional, late-stage security model has several critical downsides in a modern, agile environment. Costly remediation. The later a vulnerability is discovered in the development lifecycle, the more expensive and time-consuming it is to fix. A flaw found in production can be exponentially more costly than one caught during design or coding. Slows down releases. Manual security reviews or penetration tests at the end of a rapid release cycle become bottlenecks, negating the speed benefits of CI/CD. Increased attack surface. As software becomes more distributed, microservices, cloud-native, and releases become more frequent, the potential attack surface grows. Security as an enforcer. When security is a separate checkpoint, it can be perceived as an obstacle by development teams, leading to friction and circumvention of processes. Compliance pressures. Regulatory requirements, GDPR, HIPAA, PCI DSS, etc., demand robust, auditable security practices. DevSecOps addresses these challenges by making security a shared responsibility and an inherent part of the entire value stream. Key DevSecOps practices and security as code. DevSecOps isn't about adding more manual steps. It's about integrating and automating security activities within the existing DevOps pipeline. This often involves treating security policies and controls as code so they can be version controlled, tested, and automated. Security by design, shift left in design planning, threat modeling. At the design phase, identify potential threats and vulnerabilities to the application and its underlying infrastructure. This structured approach helps proactively build in security controls. Security requirements. Explicitly define security requirements alongside functional requirements, ensuring they are considered from the outset. Secure coding practices. Developers are trained in secure coding standards and principles. Automated security testing. Shift left in CI/CD. These tools are integrated directly into the CI/CD pipeline, providing rapid, continuous feedback on security risks. Static application security testing, SAST, scans source code, bytecode, or binary code without executing the application. It looks for common coding flaws and vulnerabilities, e.g., SQL injection, cross-site scripting. SAST tools run early in the CI process, providing fast feedback to developers. Dynamic application security testing, DAST, tests a running application from the outside by simulating attacks. DAST tools are often integrated later in the pipeline, e.g., in staging environments to identify runtime vulnerabilities and configuration issues. Software composition analysis, SCA, scans for known vulnerabilities in third-party libraries, open-source components, and dependencies used in the application. Given the heavy reliance on external libraries, SCA is crucial. Infrastructure as code, ISC security scanning. Scans ISC templates, Terraform, CloudFormation, etc., for misconfigurations that could lead to vulnerabilities, e.g., open S3 buckets, overly permissive security groups. Container image scanning. Scans Docker images or container registries for known vulnerabilities within the OS, libraries, or application components packed into the image before deployment. Secrets management. Securely managing sensitive information like API keys, database credentials, and certificates, ensuring they are not hard-coded but injected securely at runtime. Tools like HashiCorp Vault, AWS Secrets Manager, or Azure Key Vault are essential here. Security in production, shift right. While shifting left is key, security doesn't end at deployment. Production environments still require continuous monitoring and defense. Security monitoring and logging. Comprehensive logging and monitoring, as discussed in Chapter 8, with a focus on security-relevant events, e.g., failed login attempts, unusual network traffic, unauthorized access. Incident response and forensics, having a clear, well-rehearsed plan for detecting, responding to, and recovering from security incidents. Runtime protection, e.g., WAF RASP. Web application firewalls, WAFS, and runtime application self-protection, RASP, Solutions can provide an additional layer of defense against attacks. Cultural shift. Security as everyone's responsibility. Just like DevOps itself, DevSecOps is fundamentally a cultural shift. It requires shared ownership. Security becomes everyone's concern, from developers to operations, rather than solely the responsibility of a dedicated security team. Collaboration. Security teams work with development and operations, providing guidance, education, and tools, rather than being a bottleneck or an auditor. Education and training. Equipping developers and operations staff with the knowledge and skills to identify and manage security risks. Metrics for security. Measuring security posture, vulnerability remediation rates, and security test coverage to drive continuous improvement. Consider QuickShip Logistics again. Initially, their security team performed manual penetration tests once a year, often holding up major releases due to late-stage findings. With DevSecOps, they implemented SASD scans integrated into every pull request build, providing immediate feedback on code defects. SCA tools to automatically check for vulnerable open-source dependencies in their CI pipeline. ISC scanning for their Terraform templates, ensuring their cloud infrastructure was compliant and hardened before deployment. Regular security training for their development teams on common vulnerabilities and secure coding practices. Automated container scanning before deployment to production. This shift didn't make the security team redundant. Instead, it freed them from reactionary firefighting to focus on higher-value activities like threat intelligence, architecture reviews, and advanced security research. They became enablers of security, embedded within the development teams. DevSecOps transforms security from a traditional, no department into an enabler, allowing organizations to deliver secure software at the speed of business. By integrating security into the DNA of the DevOps pipeline, companies can achieve what once seemed contradictory: rapid innovation and robust security. However, no amount of automation or integrated testing can succeed without the right people, with the right mindset, working together. This leads us to the most vital aspect of true DevOps transformation: the human element. 10. The human element: culture, communication, and transformation. We've explored the technical pillars of DevOps: version control, continuous integration, continuous delivery, infrastructure as code, robust feedback loops, and integrated security. These are powerful tools and practices that accelerate software delivery and improve quality. However, the most sophisticated automation, the smartest pipelines, and the most comprehensive testing suites count for little if the underlying human dynamics are flawed. DevOps, at its core, is a people problem, not a technology problem. It is a cultural movement that demands fundamental shifts in how people interact, communicate, and collaborate. This chapter delves into the human element, the subtle yet critical factors of culture, communication, and leadership that truly drive successful DevOps transformation. DevOps is people first. The most challenging aspect. Remember the wall of confusion between development and operations. That wall wasn't built with bricks and mortar. It was constructed from misaligned incentives, different priorities, lack of empathy, and poor communication. DevOps aims to dismantle that wall. Yet, it's often easier to adopt a new tool than to change entrenched behaviors or organizational structures. Many organizations invest heavily in DevOps tools but fail to achieve their desired results because they neglect the cultural transformations required. Breaking down silos towards cross-functional teams. Traditional IT structures often organize teams into functional silos: a development team, an operations team, a QA team, a security team. While this can foster deep specialization, it inherently creates handoffs, bottlenecks, and fragmented responsibilities. In a DevOps world, the goal is to shift towards cross-functional teams where members from different disciplines work together on a shared product or service. Shared goals and metrics. When developers, operators, security specialists, and QA engineers are all part of the same team, they share common goals, e.g., product availability, feature velocity, customer satisfaction, system stability. This naturally aligns incentives and fosters shared ownership. Empathy and understanding. Working side by side helps team members understand each other's challenges and perspectives. Developers appreciate the complexities of running systems in production. Operations personnel understand the pressures of rapid feature delivery. This mutual understanding builds bridges where walls once stood. For instance, a developer might spend a day observing the operations team responding to production incidents, gaining invaluable insights into the runtime realities of their code. Conversely, an operations engineer might pair program with a developer on a new feature, learning firsthand about the development process. Embedded specialties. Rather than a separate QA team at the end of the line, a QA specialist is embedded within the product team, ensuring quality is built in from the start. Similarly, a security champion or operations engineer might be part of the development cycle, providing guidance and integrating security and operational concerns early. Facilitating communication. The lubricant of collaboration. Effective communication is the lifeblood of cross-functional teams. DevOps thrives on open, transparent, and frequent communication. Open channels, encouraging direct communication over formal tickets or lengthy email chains. Chat platforms, Slack, Microsoft Teams, become central hubs for rapid, informal communication and problem-solving. Transparency, making information readily available. This includes sharing dashboards, observability, pipeline statuses, CI/CD, and backlog priorities, planning. Active listening, encouraging team members to truly hear and understand each other's perspectives, fostering constructive dialogue rather than defensive arguments. Knowledge sharing, beyond formal documentation, encouraging pair programming, mob programming, internal presentations, and rotation programs, where developers spend time with ops, and vice versa, to organically spread knowledge and build collective expertise. The importance of psychological safety, learning from failure. In a rapidly evolving, complex environment, failures are inevitable. The critical difference in a DevOps culture is how an organization responds to those failures. Psychological safety refers to a climate where people feel safe to speak up, ask questions, share dissenting opinions, admit mistakes, and take calculated risks without fear of punishment or humiliation. Blameless postmortems. This is a cornerstone practice for fostering psychological safety. When an incident occurs, the focus is not on who made the mistake, but what happened, why it happened, systemic factors, process flaws, environmental issues, and how to prevent it from recurring. The goal is collective learning and continuous improvement, not assigning blame. Example: if a new deployment causes an outage, the postmortem report focuses on the flawed process, the inadequate testing, or the unclear documentation, rather than singling out the individual who initiated the deployment. Embracing experimentation. A culture of psychological safety encourages teams to experiment with new tools, processes, and ideas. If an experiment doesn't yield the expected results, it's viewed as a learning opportunity, not a failure. Leadership's role in DevOps transformation. DevOps is not something that can be mandated from the bottom up alone. True transformation requires active, visible, and sustained support from leadership at all levels. Leaders must champion the cause, articulate the vision and benefits of DevOps, explaining the why behind the changes. Provide resources, allocate sufficient time, budget, and personnel for training, new tools, and process changes. Lead by example. Adopt DevOps principles in their own leadership style, demonstrating collaboration, transparency, and a learning mindset. Empower teams. Delegate decision-making authority to empowered, cross-functional teams, giving them autonomy over their work. Remove obstacles. Actively identify and dismantle organizational, process, or technical impediments that hinder DevOps adoption. Celebrate small wins. Recognize and celebrate incremental successes to build momentum and demonstrate progress. Navigating resistance to change. Even with strong leadership and clear benefits, change is hard and resistance is natural. It can stem from fear of the unknown, uncertainty about new roles, responsibilities, or processes, fear of job loss, concerns that automation will eliminate roles, comfort with the status quo, people are accustomed to existing ways of working, lack of understanding, not fully grasping the full implications or benefits of DevOps. past negative experiences, previous failed change initiatives resulting in cynicism. To overcome resistance, organizations should communicate, communicate, communicate. Be clear about the vision, benefits, and how individuals' roles will evolve. Address concerns transparently. Listen to fears and offer concrete solutions or reassurance. Provide training and support. Equip people with the new skills and knowledge required. Start small and show success. Implement DevOps in a pilot project, demonstrating tangible benefits and building internal champions. Involve people in the change. When people feel they have a say in the change, they are more likely to support it. The journey towards a DevOps culture is iterative and ongoing, much like the software delivery process itself. It demands patience, empathy, and a deep understanding that technology merely facilitates change. It doesn't create it. True transformation arises from the willingness of people to break down silos, communicate openly, learn from mistakes, and relentlessly pursue shared goals. This human alignment, in turn, provides the context and motivation for effectively measuring the impact of DevOps on organizational performance, which is the focus of our next chapter. 11. Measuring what matters. Metrics and ROI in DevOps. We've covered the cultural shifts, the automation magic, and the collaborative spirit that define DevOps. But how do you know if all this effort is actually paying off? How do you demonstrate the value of transforming your organization's software delivery process? The answer lies in measurement. In a DevOps environment, data-driven decision-making is paramount. Metrics serve as your compass, telling you where you are, where you're going, and what needs improvement. They help inform decisions, justify investments, and ultimately prove the return on investment, ROI, of your DevOps initiatives. Why measure? Beyond simply justifying budget, metrics in DevOps serve several critical purposes. Inform decisions. Data helps identify bottlenecks, pain points, and areas for automation or improvement. It shifts discussions from opinions to facts. Demonstrate value. Quantifiable improvements are essential for communicating success to stakeholders, business leaders, and across teams. Identify bottlenecks. By analyzing the flow of work, you can pinpoint stages that are slowing down the entire pipeline. Drive continuous improvement. Metrics highlight trends, allowing teams to set targets, experiment with changes, and track their impact. Foster accountability, system-wide. Metrics apply to the entire value stream, fostering shared accountability rather than isolated blame. It's crucial to measure what truly matters for your business outcomes, rather than simply collecting data for its own sake. Focus on actionable insights, not vanity metrics, that look good but don't drive real change. The 4 key metrics, DORA metrics. Extensive research, most notably from the DevOps Research and Assessment, DORA team, whose findings are published in the State of DevOps Report and the book Accelerate, has identified 4 key metrics that are highly correlated with organizational performance and effective software delivery. These are often referred to as the DORA metrics. Lead time for changes. Definition: the time it takes for a change to go from code committed to code successfully running in production. This measures the speed of your entire value stream. What it tells you: shorter lead times indicate a highly efficient, automated, and collaborative pipeline. It reflects how quickly your organization can translate an idea into value for the customer. Improvement focus. Reducing manual steps, improving CI/CD pipeline efficiency, reducing batch sizes. Deployment frequency. Definition: how often an organization successfully releases to production. What it tells you: higher deployment frequency typically means smaller, less risky changes. It also indicates a high degree of automation and confidence in the deployment process. Improvement focus. Automating deployments, improving testing, using feature flags to decouple deployment from release. As discussed in Chapter 6. Change failure rate. Definition: the percentage of deployments to production that result in a service degradation, e.g., outages, impaired functionality, and require remediation, e.g., hotfix, rollback, patch. What it tells you: a lower change failure rate signifies higher quality, more robust testing, Chapter 5, and effective risk mitigation. Improvement focus. strengthening automated testing, better monitoring, implementing advanced deployment strategies, canary, blue-green, and thorough postmortem processes. Mean time to restore MTTR. Definition: the average time it takes to restore service after a service degradation or unplanned outage. What it tells you: a shorter MTTR indicates highly effective incident response, clear runbooks, rapid diagnosis capabilities, observability, Chapter 8, and good rollback procedures. It's a measure of resilience. Improvement focus: enhancing observability, blameless postmortems, automated rollbacks, and effective communication during incidents. These 4 metrics provide a holistic view of your software delivery performance. High-performing organizations excel in all 4, achieving rapid delivery of features with high quality and resilience. Additional useful metrics: while the DORA metrics are foundational, other metrics can provide valuable insights depending on your context. Test automation coverage: the percentage of your codebase or functionalities covered by automated tests. Higher coverage gives more confidence in changes. Cycle time: similar to lead time, but often measuring the time from when work starts on a feature to when it's delivered. Application performance metrics: beyond traditional infrastructure metrics, focus on end-user experience, e.g., page load times, API response times, application error rates. Security vulnerability remediation time: how quickly identified security vulnerabilities are addressed and patched. Team satisfaction, employee engagement: happy, engaged teams are more productive and innovative. Surveys and sentiment analysis can provide qualitative and quantitative insights into the human element, Chapter 10. Cost of change: the actual monetary cost associated with implementing and deploying a new feature or change. Calculating return on investment, ROI, in DevOps. Demonstrating the explicit ROI of DevOps can be challenging, as many benefits are qualitative or impact entire systems rather than isolated features. However, it's crucial for gaining sustained executive buy-in. ROI can be framed in several ways: cost savings, reduced rework. Fewer bugs caught late means less time spent fixing them. Reduced downtime. Faster MTTR and lower change failure rates mean less lost revenue or productivity due to outages. Optimized resource utilization. Efficient infrastructure provisioning and auto-scaling can lead to lower cloud costs. Lower opportunity cost. Faster delivery means features reach the market quicker, potentially capturing more revenue or market share. Increased revenue market share. Faster time to market. Getting features into customers' hands quicker can lead to competitive advantage and increased customer satisfaction. Experimentation and innovation. The ability to rapidly test new ideas and pivot based on feedback can lead to innovative products and services. Improved quality and reliability. Enhanced customer satisfaction. Fewer bugs and outages translate directly to happier customers. Stronger brand reputation. A reputation for reliable, high-quality software builds trust. Employee satisfaction and retention. Reduced burnout. Automation reduces repetitive, tedious tasks. Blameless culture reduces stress. Increased engagement. Teams feel more empowered and productive. Attraction, retention of talent. High-performing tech organizations are attractive places to work. Storytelling with data. When presenting metrics and ROI, it's not enough to just show numbers. Businesses respond to stories. Connect the numbers to qualitative benefits. For example, instead of just saying deployment frequency increased by 400%, explain how that allowed the marketing team to run weekly A/B tests on new features, leading to a 15% increase in user engagement, or how it enabled the sales team to close a major deal by demonstrating responsiveness to customer needs. Consider QuickShip Logistics and their transformation. Before DevOps, they released quarterly, with many late-night deployments resulting in frequent outages, high change failure rate, high MTTR. Their lead time for changes was months. After implementing DevOps, lead time reduced from months to days. This meant they could respond to competitor features or customer requests in weeks, not quarters. Deployment frequency increased from quarterly to multiple times a week. Change failure rate decreased by 80% due to better testing and smaller, more controlled deployments. MTTR reduced from hours to minutes due to automated rollbacks and improved observability. These improvements directly translated into quantifiable value: increased customer satisfaction, fewer outages, higher revenue, faster feature delivery, and improved employee morale, less crunch time, more confidence. Measuring what matters is essential for proving the value of DevOps and for guiding its continuous evolution. By focusing on these core metrics and tying them to business outcomes, organizations can build a compelling case for their transformation journey. However, even with the best metrics, the journey is rarely without bumps. Understanding common pitfalls and how to navigate them is the focus of our next discussion. 12. Navigating the challenges, common pitfalls, and how to overcome them. By now, you understand the immense power and promise of DevOps. Its principles, processes, and tools offer a clear path to faster, more reliable, and more secure software delivery. However, the path to successful DevOps adoption is rarely smooth or without its bumps. Many organizations embark on a DevOps journey only to encounter significant hurdles or missteps that hinder their progress. Understanding these common pitfalls is crucial to anticipating them, avoiding them, or successfully navigating them once they arise. Common obstacles on the DevOps journey. Cultural resistance. This is, by far, the most significant and pervasive challenge. As we discussed in Chapter 10, DevOps is a cultural transformation first and foremost. That's not my job mentality. Individuals may resist taking on new responsibilities or collaborating with teams they previously had little interaction with. Operations may feel their expertise is being diminished. Developers may resent being on call for production issues. Fear of automation. Concerns that automation will eliminate jobs or make human skills irrelevant. Comfort with the status quo. People naturally resist change, especially when existing processes, however inefficient, feel safe and familiar. Siloed incentives. If departments are measured and rewarded differently, e.g., developers for features, operations for uptime, their incentives will clash. Tooling overload/misguided focus on tools. Shiny tool syndrome. Organizations become fixated on acquiring the latest and greatest DevOps tools without first understanding their underlying problems or the principles those tools are meant to enable. They buy a CI/CD pipeline without having the culture or practices, like frequent commits or automated testing, to support it. Big bang tool adoption. Trying to implement too many new tools at once, leading to complexity, confusion, and a steep learning curve. Tooling proliferation. Different teams adopting different tools for similar purposes, leading to fragmentation and difficulty in collaboration or standardization. Legacy systems and technical debt. Monolithic applications. Large, tightly coupled applications are difficult to break down, test, and deploy frequently. Their sheer complexity often makes automated testing and deployment challenging. Manual processes and dependencies. Older systems may have manual dependencies that are deeply embedded, making true automation difficult. Dependency on niche skills. Legacy systems often rely on outdated technologies or highly specialized knowledge, slowing down modernization efforts. Lack of leadership buy-in and support. Insufficient resources. Without executive sponsorship, teams may lack the necessary budget, time, or personnel to drive the transformation. Focus on short-term gains. Leaders may demand immediate, dramatic results, overlooking the long-term, iterative nature of DevOps transformation. Lip service DevOps. Leaders declare an intention to do DevOps, but fail to enact the necessary organizational or cultural changes required to support it. Skill gaps and training deficiencies. Cross-functional knowledge. Developers might lack operations knowledge. Operations staff may lack coding or testing skills. DevSecOps requires security literacy from all. New tools and technologies. Learning new CI/CD platforms, ISC languages, monitoring tools, and security scanning tools. Lack of dedicated time for learning. Teams are often too overloaded with day-to-day work to dedicate time to upskilling. Frankenstein pipelines. Brittle automation. Pipelines that frequently break, are hard to debug, or provide inconsistent results, leading to a lack of trust in automation. Overly complex pipelines. attempting to automate too much too soon, leading to an unmanageable and unmaintainable pipeline. Lack of standardization. Different teams building their pipelines in different ways, making it hard to share best practices or common modules. Neglecting security or treating DevSecOps as an afterthought. Security as a bottleneck. Not integrating security early, leading to late-stage findings that require expensive rework or slow down releases. Lack of automation in security, relying solely on manual security reviews and penetration testing. Insufficient awareness, development and operations teams lacking sufficient security knowledge. Burnout and change fatigue. Doing too much too soon. Trying to implement all DevOps practices and tools simultaneously can overwhelm teams. Unrealistic expectations. Setting unrealistic goals or timelines for transformation. Neglecting team well-being. Focusing solely on metrics and delivery speed without considering the human cost. Strategies for overcoming challenges. Recognizing these pitfalls is the first step. Actively mitigating them is the key to success. Start small, prove value, and iterate. Pilot projects. Begin with a small, manageable project or a single team. Demonstrate tangible, measurable benefits. Walking the wall. Find one small, high-friction point between dev and ops and try to streamline it. Celebrate small wins. Publicly acknowledge and celebrate successes, no matter how small, to build momentum and internal champions. Focus on principles first, tools second. Understand the why. Ensure everyone understands the underlying principles of DevOps, CALMS, 3 ways before adopting tools. Tooling as enablers. Choose tools that support your desired processes and culture, rather than letting tools dictate them. Start with simpler tools and evolve. Invest in education and cross-skilling, formal training. Provide training on new tools, coding practices, and security principles. Cross-pollination programs. Implement rotation programs, devs in ops, ops in dev, and encourage pairing to foster empathy and knowledge sharing. Communities of practice. Create forums where engineers from different teams can share knowledge and best practices. Secure strong leadership buy-in and sponsorship. Educate leaders. Clearly articulate the business value and long-term benefits of DevOps, not just the technical aspects. Use the DORA metrics to tell a compelling story. Active participation. Leaders should visibly champion the transformation and remove organizational roadblocks. Long-term vision. Emphasize that DevOps is a journey of continuous improvement, not a one-time project. Embrace incremental change and automation. Automate progressively. Don't try to automate everything at once. Identify the most painful manual steps and automate them first. Version control everything. Treat configuration, infrastructure, and even documentation as code, making it testable and repeatable. Build resilient pipelines. Invest in making your CI/CD pipelines robust, reliable, and easily maintainable. Integrate security from the start, DevSecOps. Shift left security. Integrate automated security testing into every stage of the pipeline. Security champions. Designate individuals within development teams who become security advocates and experts. Collaborate with security teams. Bring security professionals in as partners and enablers, not just auditors. Foster a culture of psychological safety and learning. Blameless postmortems. Practice blameless analysis of incidents to promote learning from failures. Embrace experimentation. Encourage teams to try new things, even if some experiments don't succeed. Communicate transparently. Share successes and failures openly. Prioritize technical debt strategically. Dedicated time. Allocate specific time in sprints or cycles to address technical debt, e.g., refactoring monoliths, modernizing outdated systems. Value-driven decisions. Prioritize refactoring that directly impacts new feature development or system stability. The journey to DevOps is a marathon, not a sprint. It's filled with learning, adaptation, and continuous refinement. By understanding these common challenges and proactively implementing strategies to overcome them, organizations can effectively navigate their transformation, unlock the full potential of DevOps, and build a resilient foundation for the future. The landscape of technology is always evolving, and DevOps must evolve with it. Our final chapter will gaze into the crystal ball, exploring the emerging trends that will shape the DevOps of tomorrow. 13. Beyond tomorrow. Emerging trends and the future of DevOps. We've traversed the landscape of DevOps, from its historical roots and foundational principles to its practical implementation across the software delivery pipeline, and we've even explored the human elements and common challenges. But technology is a relentless current, always pushing forward. DevOps, as a dynamic philosophy, is continuously evolving to meet new demands and leverage emerging technological advancements. This chapter peers into the future, exploring trends that are already shaping the next generation of DevOps practices. 1. AI Ops, intelligence for operations. As systems grow in complexity and volume of data metrics, logs, traces, becomes overwhelming, human operators struggle to make sense of it all. AI Ops, artificial intelligence for IT operations, seeks to solve this by applying machine learning and artificial intelligence to IT operations data. Key capabilities: anomaly detection, automatically identifying unusual patterns in system behavior that might indicate impending issues, often before they impact users. Root cause analysis, speeding up incident resolution by correlating events across disparate data sources and suggesting probable causes. Predictive analytics, forecasting potential outages or performance bottlenecks based on historical data and trends. Intelligent alerting, reducing alert fatigue by suppressing redundant alerts and prioritizing critical ones, sending only actionable notifications to on-call teams. Impact on DevOps. AI Ops enhances the measurement and feedback pillars of DevOps, making operations more proactive, efficient, and resilient, allowing human operators to focus on problem-solving rather than data sifting. 2. GitOps, operations through Git. GitOps takes the principles of infrastructure as code, Chapter 7, and extends them to the entire operational workflow. It uses Git, the version control system, as the single source of truth for declarative infrastructure and application configurations. How it works. Instead of directly modifying production infrastructure or deploying applications using manual scripts, all changes are made by submitting pull requests to a Git repository. An automated process then observes this repository and ensures that the live infrastructure and application deployments match the desired state defined in Git. Key benefits: auditability. Every change to production is captured as a commit in Git, creating a complete audit trail. Security. Changes are reviewed and approved via Git's pull request mechanism, enhancing security. Rollback. Easily revert to any previous state by simply reverting a Git commit. Consistency. Ensures configuration parity across environments. Impact on DevOps. GitOps strengthens the automation, lean, and sharing aspects by unifying all operational changes under version control, making them more transparent, secure, and collaborative. 3. Serverless and functions as a service, FaaS, shifting operational burden. The rise of serverless computing, particularly FaaS platforms like Oz Lambda, Azure Functions, and Google Cloud Functions, fundamentally alters the operational responsibilities for development teams. Key change: developers write code for individual functions, and the cloud provider handles almost all the underlying infrastructure management. Scaling, patching, provisioning, load balancing. This means developers can focus solely on business logic. Impact on DevOps, reduced ops concerns. Many traditional operations tasks, server maintenance, instance scaling, are abstracted away. New ops concerns. Focus shifts to monitoring function execution, cost optimization, debugging distributed serverless architectures, and managing event triggers. Faster iteration. Simpler deployment models for functions can lead to even faster delivery cycles. Future implications. DevOps practices will adapt to include serverless native, CI/CD pipelines, specialized monitoring for function execution, and security practices tailored to highly granular, event-driven architectures. 4. Site reliability engineering, SRE, a disciplined approach to DevOps. While DevOps is a broad philosophy, site reliability engineering, SRE, pioneered by Google, can be seen as a specific, highly prescriptive implementation of DevOps principles. particularly focused on large-scale, highly reliable systems. Key principles: embracing risk, using error budgets to balance reliability with innovation, eliminating toil, automating repetitive, manual operational work, monitoring and observability by default, treating systems as observable black boxes, blameless postmortems, a rigorous approach to learning from incidents, shared ownership, developers have stakes in production reliability, relationship to DevOps. SRE is how Google does DevOps. It provides a specific set of practices and a cultural blueprint for achieving extreme levels of reliability and operational efficiency. The future will see more cross-pollination between SRE and broader DevOps practices. 5. Platform engineering, building internal developer platforms. As organizations grow, enabling thousands of developers to work efficiently on a diverse set of microservices and cloud infrastructure becomes a challenge. Platform engineering addresses this by building internal developer platforms. Concept: a dedicated team builds and maintains a robust, self-service platform that abstracts away infrastructure complexities and provides developers with standardized tools, templates, and guardrails for building, deploying, and operating applications. Benefits: increased developer velocity. Developers can focus on business logic rather than infrastructure concerns. Consistency and compliance ensures applications adhere to security, operational, and architectural standards. Shared best practices codifies and embeds organizational best practices into the platform. Impact on DevOps reaffirms DevOps sharing and automation principles. It extends the CI/CD pipeline to include platform development itself, allowing the delivery of consistent, enterprise-grade development environments as a service to internal teams. The continued importance of culture. While technology will continue to advance at a dizzying pace, one thing remains constant: the human element. The core cultural principles of DevOps, collaboration, empathy, shared responsibility, feedback, and continuous learning will remain paramount. New technologies merely provide new avenues and opportunities for these principles to be applied. The future of DevOps will continue to be about breaking down new silos, Dev versus AI ML Ops, platform teams versus product teams, fostering even greater levels of automation and intelligence, and continuously refining the balance between speed, quality, security, and human well-being. It's a journey of infinite continuous improvement. 14. Your DevOps journey, a call to action. We have reached the end of our exploration into DevOps, a philosophy and set of practices that have fundamentally reshaped how organizations deliver software. We began by dismantling the wall of confusion between development and operations, understanding the historical friction that necessitated a new approach. We then navigated the core principles that serve as the DevOps compass, the CALMS framework and the 3 ways, emphasizing culture, automation, lean principles, measurement, and sharing. From there, we delved into the practical mechanics of the DevOps pipeline, the essential foundation of continuous flow, collaboration, and robust version control. The automated assembly line of continuous integration, ensuring frequent, reliable code merges. The critical checkpoints of continuous testing, verifying quality at every stage. The seamless delivery mechanisms of continuous delivery and deployment, getting validated software into users' hands rapidly. The power of infrastructure as code to build resilient and repeatable environments. The crucial feedback loop provided by monitoring, logging, and observability, illuminating system health and performance. The integral role of DevSecOps, embedding security into every facet of the pipeline. We then turned our attention to the often underestimated yet profoundly critical human element, emphasizing how culture, communication, and psychological safety are the true drivers of transformation. We acknowledged the importance of measuring what matters, using data-driven insights like the DORA metrics to prove ROI and guide continuous improvement. Finally, we looked ahead, identifying emerging trends like AI ops, GitOps, and platform engineering, proving that DevOps is a dynamic, ever-evolving discipline. The continuous journey. If there's one overarching message to take from this book, it is this: DevOps is not a destination, It is an ongoing journey of continuous improvement. You don't do DevOps once and then declare victory. It's an iterative process, much like agile development itself, focused on constantly optimizing the flow of value from idea to customer satisfaction. Your organization's DevOps journey will be unique. It will encounter specific challenges related to your legacy systems, organizational structure, leadership styles, and industry regulations. There's no single, prescriptive recipe that works for everyone. However, the foundational principles and practices outlined in this book provide a robust framework that can be adapted and applied to virtually any context. A call to action, your next steps. So, where do you begin? How do you translate the concepts in this book into tangible action within your own organization, team, or even your individual role? Here are some actionable suggestions. Start small, think big. Don't try to change everything at once. Identify a single, high-friction problem in your current process. Perhaps it's slow environment provisioning, manual deployments that frequently fail, or a frustrating lack of visibility into production issues. Pick one such pain point and focus your initial DevOps efforts there. Automate one small, repetitive task. Get a quick win and build momentum. Find a fellow traveler. DevOps is a collaborative endeavor. Look for others within your organization who are equally frustrated by the old way of doing things or who are passionate about improving how you deliver software. This could be a developer eager for faster feedback, an operations engineer burdened by manual toil, or a QA specialist tired of late-stage bug discoveries. Form a small, cross-functional working group and champion change together. Bridge the communication gap. If you're a developer, spend time talking to your operations colleagues about their challenges and vice versa. Ask clarifying questions. Seek to understand their perspective. True empathy is the first step in breaking down silos. Start an informal coffee meetup where different teams can simply chat and share insights. Embrace version control truly. If you're not already doing so, ensure everything is in version control. Application code, build scripts, test scripts, infrastructure definitions, infrastructure as code, and even documentation. This is the bedrock upon which all other automation and collaboration are built. Automate one thing, pick a single manual task that is repetitive and error-prone. Can you write a script for it? Can you include it in an existing automated process? Every piece of automation, no matter how small, contributes to the continuous flow. Seek feedback and act on it. Whether it's from your automated pipelines, seeing a red build, your monitoring tools a spike in errors, or your customers a bug report, pay attention to feedback. Don't just dismiss it. Understand why it happened and use that insight to improve. Implement at least one aspect of blameless postmortems after an incident. Keep learning. The technology landscape is constantly changing. Read articles, attend webinars, participate in online communities, or pick up one of the foundational books listed in the further reading section, like the Phoenix Project or the DevOps Handbook. Stay curious and open to new ideas. Be patient, be persistent. DevOps transformation takes time, effort, and resilience. There will be setbacks, resistance, and moments of doubt. Celebrate the small victories, learn from the challenges, and maintain your commitment to the long-term vision. Your DevOps journey is not just about building better software faster. It's about building better teams, fostering a healthier organizational culture, and ultimately, delivering more value to your customers and your business. The principles of DevOps equip you to navigate the complexities of the modern digital world with confidence and agility. The future of software is continuous, collaborative, and ever-improving. You now have the compass and map to join that journey. The time for action is now.